This is an example of an analysis of variance, a one-way analysis of variance, or ANOVA, and this will be done with planned contrasts. The problem is looking at a researcher wanting to test three different study break strategies and see how they influence students' test performance. She randomly assigned students to one of these conditions before giving them a test of problem-solving skills. Group 1 had a 10-minute social media break. Group 2 had a 10-minute walk outside, and Group 3 had a 10-minute quiet rest. You can see the mean and variance for each of these are listed. And she does have a hypothesis that students taking the social media break would perform worse than those who had walked outside or rested quietly. We're asked to conduct an ANOVA to find out the omnibus F score and then conduct planned contrast in accordance with this hypothesis stated in the previous sentence. So let's begin by parsing the problem. Population 1 are students with a 10-minute social media break. Population 2 are students with a 10-minute walk outside. And population 3 is students with a 10-minute quiet rest. Our dependent variable are test scores. Our research hypothesis states that the mean test scores will differ by break type. And our research hypothesis, our null hypothesis, is just the opposite of that. It says that mean test scores will not differ by break type. And I'm going to get rid of all the bold in here. I don't think we need that. Okay. We describe the comparison distribution. We know it's an F distribution, and we have to state the degrees of freedom. So let's go ahead and get some data from the problem in order to do this. I'm actually going to put the 9 in here and then put a formula equals this. Even though it's very simple math, this will allow me to copy paste. And I'll put the mean in here, which is 90.5, and the EVAR, which is 54.3. And I'm going to go ahead and get that for each of these. 11 we have for the N for the second group. The mean is 107.8. I'm just gathering these right from the problem, and the estimated variance is 57.6. And finally, we have N3, which is 10 individuals in the sample. The mean is given as 99.4, and the estimated variance is 49.2. I'm going to copy this formula into each of these so that we just save a little bit of time. Let's begin then by getting the shape of the comparison distribution. It's the F distribution, and we first state the degrees of freedom for the group. So let's go ahead and get that. We have 3 groups, and we know the DF between will be this 3 minus 1. To get our degrees of freedom, we can get it 2 ways. We can either just sum the degrees of freedom across these groups. So now I've typed in sum, and I'm just going to copy this range in there, and we get 27. Another way we could do this, depends on what's easier in a given situation, is we could sum all of these n's, and we could subtract the number of groups. And we also get 27. So either way we want to do it, we know that we have 27. So the F distribution that we look for is going to be an F distribution with 2 and 27 degrees of freedom. We next look up the cutoff point for that F ratio. And so we get out our critical value tool, and we need to make sure we're selecting the F test. We're testing at 0.05. Our numerator was 2, and our denominator, let me check and make sure. Our denominator is this DF within, which is 27. So here we go with our 27, and let's calculate. And we know that all of our F tests are always going to be positive numbers, and they're going to be one-tailed high. So we'll grab this number and 3.3541 is our cutoff point. I am not requiring you to, I'm going to put this right here and also right here. So that's going to be our cutoff point, actually. Let me preserve the formatting here. I'm going to just use this thing so we preserve the nice formatting. I don't know why I care about that, but I always seem to like the formatting. All right, our next step is to calculate the F ratio. But before we do that, let me draw on this F distribution what that cutoff point is going to look like. I don't have my screen on with my pen right now, so let me use the insert menu to create a, just to draw a line on here where the cutoff point is going to be. So we have a 3.3541, which is going to fall right about here. And what that means is that the reject region, let's draw this like so, is going to fall into this tail. So in a nutshell, we're just looking for having a cutoff point, having a score that is greater than that 3.3541. We can insert that there. F alpha equals 3.35. So that's what this looks like just for the sake of understanding it. Our reject region is this shaded region right here. And our fail to reject region, let's just increase the transparency there. Our fail to reject region is going to be the rest of the distribution. All right, so let's continue on then. So we have looked up our cutoff point, and now we're going to figure out F observed. And you'll recall from the lecture that this is the same as F sample. The more proper way to write it is F observed, which is why I've changed it. So the way we've done this in class is we've gone ahead and calculated weight. And you can see here that the weight is all written out for us. It's df1 divided by df within. It's the same way we used to calculate proportions when we were doing our independent samples t-test. So let's go ahead and get our df1 divided by df within. And so that says that about 29% of the scores are going to be in this condition 1. It's based on just strictly the overall number in the sample. And I'm going to hold that steady by putting the $ in between both the column and the row. And that will allow me to copy and paste across these conditions. And so we know that E bar W1 is just E bar 1 times the weight. So let's go ahead and calculate that. Weight times E bar 1. And that's what we'll be using to calculate our within group variance. Let's copy this and paste it over and check if our formula looks good. So we know that we wanted to take and divide our df2 by df within, which we did, and we knew we wanted to multiply these, which also looks good. So we're in good shape with these calculations. We can go down here to our within group variance. We can see MS within is the sum of all the variances across conditions. And let's go ahead and get those. Sum of all those EVAR weighted, and we get 53.822. Now, since all of our, never mind, and that's where we'll stop. Okay, let's continue on then. We have 3 conditions in our example. Our next step is to calculate our between groups variance, and to do so, we have to calculate our squared deviations for MS between. To get our squared deviations, we only have 3 groups, so I'm going to get rid of that M4. Let's go ahead and copy the means out for each of these conditions. So mean 1 is right here. Let's pull it down where we can use it. Mean 2 is right here. And mean 3 is right here. So now our means are ready. Let's also grab the ends, because we're going to need these in the last step. This is just a slightly modified procedure. And you'll see how we're going to use that M. We've already gone through it in the lecture. Next, we have to calculate what we call our grand mean, which is just the average of all those means we just calculated. we can use our average formula. Here we go. And now we have our grand mean calculated. Next, we calculate our deviations because we're getting an SS. It's a little bit different sum of squares because we're going to multiply by n first, but other than that, it's just the same. So we can go ahead and get our deviations, which is each mean minus the grand mean. I'm going to mark both actually, I'm just going to mark put the $ in before the row so that it holds steady as we work down. And now that allows us to copy paste. I think I'll go ahead and square first, and then I can do the copy paste all at once. And I think I'll multiply by n also, and then I can do that copy paste as well. So we take our squared deviations and we multiply by n. And that's what's different about this formula. Normally, when we calculate sum of squares, we would go this far and then we would sum them. Now we're going to sum this column. We're multiplying our squared deviation times n. I'll highlight there so you can once again see the formula. Squared deviation times n. Now we should be able to copy and paste this down. Although, as always, we'll want to be careful to double check. Let's make sure that we properly subtracted mean minus grand mean. And it looks like we didn't. So it's a really good thing we did this. So let's go ahead and correct our error. Here we needed to click on M, and instead we clicked on N. So let's fix that error, and let's copy that all the way down. Now let's see if that's any better. And that looks a lot better. We now have each score subtracting the grand mean. That looks good. Let's make sure this one is correct. Did I square the right number? And it looks like I did. This is the column that should be squared. Let's make sure I multiplied properly by n. And here we do have the squared deviation times n. All of these look really good. Now we can go ahead and sum that column. And again, we're summing this last column. We're taking our squared deviation and multiplying it by n. And finally, our last step, here's our MS between formula, is SSN, and that's just referring to that sum squared deviations times n. SSN times divided by DF between. We're calculating a variance. We have to divide. And where is our DF between? Here it is. And this is going to be our mean square between in this example. So let's go ahead then. We're ready to calculate our F ratio. We could rewrite these here if we wanted to. We don't need to. I think they're pretty clear over here. Here's our cutoff point. Now we calculate. You can see here that our formula F observed is going to be MS between divided by MS within. So let's go ahead and get that. Equals, here is our MS between, and we're dividing by MS within to get that ratio. And we find out that our F observed is 13.8788. We'll just round that off to. And so from here, we can see that this is a pretty high F ratio. Everything appears to be solid. Let's make sure I did everything correctly here. We have the between, we have the within, all of that looks good. Let's make sure that we sum these up properly. We have all our weighted EVARs that we have summed, and our weights look good, and our EVARs themselves were given. So we have a really high score here for our sample. We'll go ahead and insert a line to show where that would fall on the map. Get our shape and get a line here for our sample. It's going to be way over here somewhere. We can see our distribution goes as high as 5. And we can say that our F observed score is going to be equals 13.88. So we're really high, very long into this shaded region. This does allow us to reject the null hypothesis. So let's first write down our F observed. And let's go ahead and write our decision and conclusion. Our decision is to reject HO. And we're going to conclude, just all we can do as an omnibus conclusion so far, we can conclude that, let's go back to our hypothesis, we've rejected the null, we can cross that off. Let's just, I don't know if they have a cross-off font in here. Yep, they do. Let's strike that off that way. There, it's crossed off. This is the one we're going to keep. So let's just write conclusion. Mean test scores differ significantly according to break type. And we can put our F statistic in parentheses. We put our 2 degrees of freedom, which was 2 and 27. We put our F statistic. Actually, I think I have enough room in this text box, equals, and we had the 13.88. And the significance we tested at is 0.05. But we know that we don't actually know much about where these differences lie. All we know is that they're different. But someone who's looking at this and wanting to figure out what they might do or act on will have a little difficulty because we don't know which of these groups were significantly different. So we're going to go ahead and do some planned contrasts. These are stated in the problem. It says that she hypothesized that students taking a social media break, that is, those in population 1, would perform worse than those who walked outside or those who rested quietly. So we're going to be comparing 1 with 2 and 1 with 3. Let's go ahead and do these planned contrasts. The first thing we'll do is we'll identify our groups. We're going to compare group 1 with group 2. Let's get the means. We have them right here. Here's the mean for group 1. I'll just hit enter. And here's the mean for group 2. We can also grab the n's. We're going to need them. You'll probably recall that we're using lowercase n's now because these refer to these groups and not the entire n that we've gathered data from. Now we can go ahead and once again figure out some of these things. We have 2 groups. So our DF between is just 1. Our DF within is the sum of, we could say, take these 2 and sum them and subtract the number of groups. 18 degrees of freedom. We can calculate our grand mean in the same way as the average of these 2 means. And our MS between is going to be this column again. I'll show you why it is. The formula is the same, but I'll show you why it is that we just stop right there. Let's go ahead and calculate these tests. Mean minus the grand mean. I'm just going to lock it in with dollar signs to allow us to copy paste. If we did it correctly, I'm sure we didn't. So let's go ahead and see where we went awry here. We have, and I did that same thing again. That's because I just added that n column, so I'm throwing myself off. Let's fix our formula there. If we did it correctly, we should have both of these the same with the only difference as the sign. So I still have some sort of an error going on there. And here I got the wrong column. So now let's subtract the grand mean. Just do them both individually, I would have saved a lot of time. Equals m minus grand mean. Just do them individually this time. And we can see here that we should always get this pattern. The numbers should be the same with the only difference being the sign. We can continue on to square these. And then we can multiply by n. We multiply the squared deviation times n for that group. And we do the same here. We should be able to get a successful copy paste. And now normally we would get a sum of squares formula right here. So let's go ahead and do that. Let's get an SSN right here, which is what we have been doing. Let's sum that column. And normally we then take this sum of squares and divide by DF between. But look at what we run into here. When we do that, we're dividing by 1, so the number is the same. So this becomes a redundant step, which is why we'll just probably stay with that. We now can, first of all, figure out our F observed. We just take this MS between and we go back to that same old MS within that we calculated earlier. So let's go equals MS between divided by MS within. And we find that we have an F score of 27, which you can picture how far out that's going to be. But we do have to look up our cutoff point. And you'll remember we have to make the Bonferroni corrected alpha, which means that we need to divide alpha by the number of tests. We have two planned contrasts, so we're going to divide alpha by 2 equals 0.05 divided by 2. And now we're going to have to use alpha 0.025 with 1 and 18 degrees of freedom. Let's get out the tool and find out what we have here. Here's our calculator. Now we have to change this to 0.025. And our numerator is only 1, and our denominator, how can I forget these so quickly? Our denominator is df within, which is 18. Close that out, jump right on this. Of course, we're always doing a right-tailed test, and we have a 5.98 for our F alpha, 5.98. Our decision has to be to reject HO. Now, if we continue on, we will find that we have to do one more planned contrast, and this one has to be between group 1 and group 3, the people who took the quiet rest. So we can follow the same procedure. Let's get our mean 1, and let's get our mean for group 3. We can get our n's for both of these groups, our n for 1, and our n for 3. We still have the 2, and we have 1, and our df within is just the sum of our, we'll do it the same way we did last time. It's just the sum of the df's for each group, but let's go ahead and take these, and then we'll just subtract the 2 groups out of there. So we have 17 this time. Our grand mean is just the average of these 2 group means. Next, we take and calculate our m minus gm. So let's get our m minus our grand mean. And I think instead of getting fancy and copy pasting, I'm just going to do these one at a time. M minus grand mean. We'll go ahead and square these. We have the correct thing because we have the same number with the only difference being the sign. Next, we multiply by n, the squared deviation times n. And this time I will just copy this down. And we get our 2 that we have to use to calculate our SSN. As before, we know that MS between is going to be just the same as our SSN because our degrees of freedom that we'd be divided by is 1. So they would be identical. So we're going to just calculate the sum of these 2, and we discover 376. We can find our F observed by taking this MS between and dividing by MS within, the one we calculated earlier. We find that we have a 6.99 for our significant number here, for our F value observed in our data. Let's check what we have for our cut points. Now we're going to still have 0.025. Now we have 1 and 17. So we'll have a slightly different threshold. We have the 0.025 here. We've selected the F value. We have 1, and now we have only 17. So let's see what we get. We get a 6.042 for our alpha, 6.042. We can see that in this case, our F observed is further into the tail than our F alpha. And so we are allowed to reject HO. Now, I haven't asked you to keep drawing these distributions, but if you're finding yourself getting muddy on what you're doing comparing these, go ahead and draw it. But in a nutshell, as long as your F observed is larger than your F alpha, you're going to reject the null. Now we're going to do what's the last little part of this, which is to write this result. And this can be a little bit tricky. I'll start a new sentence so you can clearly see what we're doing. So we could say planned contrasts. Let's tell what kind of tests we did. Revealed that students who took a 10-minute social media break performed more poorly on the test than those who took a 10-minute, what was it that they took? They took a walk outside, and those who took a 10-minute quiet rest. Now, we're going to put a couple of scores in here. This is what the sentence looks like, but let's tell what these means were. So students who took a 10-minute social media break performed more poorly on the test. And let's right here, after the social media break, let's put the mean for that group. M equals, and for that group 1, it was 90.5. So now we've told the audience what that mean was. We compare them with those who took a 10-minute walk outside. So let's tell what that mean was. And that walk outside was 107.8. And those who took a 10-minute quiet rest. And inside the period, let's put their mean. Now, we also want to tell what the F tests were for these comparison. So first we compared the ones who took a 10-minute social media break with those who took a 10-minute walk outside. So let's put the F test for that result. So we're going to put F, and then in parentheses our 1 and our 18 for our degrees of freedom. And we had that really high F observed of 27.80, always 2 decimal places, even if one of them is a 0. And we would normally tell if it was, this is probably 0.001, but we'll just leave it like this because this is what we were testing at. Later on, when we use our PSPP, we'll be able to be more specific. And let's tell the F test for this other test we did also, 1, and 17. And that F score, let's go down here, F observed was 6.99. And again, the probability was certainly less than 0.05. And that's how we would write that up. So you can just write the whole statement first and then add in those means and test results to clarify it. And that's how you'd write your official statistical decision. You can see all the formulas are written in here, and I hope they're helpful. And that is the end of this demo.